we are going to talk about how to find or construct a basis in some well-known vector spaces. Most often, you just show that the definition of vector space and then show uh, the number of elements in a vector basis is unique and etc. Then define dimension and keep going. And you also show that if given in linearly independent subset, it can be extended to a basis. But most often, students have a problem how to give a basis for a given vector space. So this is an attempt to help you solve such problems. Okay. And for more details, you should consult my book, Linear Algebra, a Geometric Approach. There will be a lot more examples and exercises, but this is just to get you started. Okay. Right. Let me share the screen. Yeah. So let us start with the first and the most important example for us, namely, suppose I have the standard Rn, the n-dimensional vector subspace, in n-dimensional space. All right. And all of you know what is known as the standard basis. Okay, this is called the standard basis, namely EI, where 0, 0, 1, 0 before, 0 later, and 0, where this one is at the ith place. This ith coordinate is 1. So this is 1 is at the ith place, at other place is 0. And if you think of Rn as a column vector, then you should write it like this: 0, 0, 1, 0. This one appears in the ith coordinate. Right? So it's we know that this collection EI 1 less than or equal to I less than or equal to n, this is a basis of Rn. It's very easy to check by definition, because any given x1, x2, xn, this is nothing other than summation xi into ei, that is x1 e1 plus xn en. Yeah. And so you have written every other vector as a linear combination of these vectors. Therefore, this is a spanning set. EI is a spanning set. And then you want to say it is linearly independent. Okay, I'm making use of my earlier video. To show it's a basis, I will show that this is a spanning set and then linearly independent. Spanning set, this shows it's a spanning set. Why it's linearly independent? Suppose some x1 e1, or if you want to call c1 e1 plus cn en equal to 0, right? Then this is same as saying this is c1 to cn, which is an element of Rn. And this is the 0 vector, 0, 0, 0. Therefore, this equal to 0, c1 cn, this equal to this. Okay. That shows that ci is 0 for all I. Therefore, we also proved it's linearly independent. And hence this is a basis. Is it clear? Okay, make sure. Now, the general thing is students do not know how to generate more bases. I will give you a very simple, easy trick. Okay, right. Let's start with R2. Right. Now I want a basis V1, V2 of R2, which is different from E1, E2. Okay. More generally, we can do that. So what I say is you write down any 2 by 2 matrix, real matrix. Right? Something like, let us say A, B, C, D, and you just put some numbers randomly. Okay, in all, okay, in most of the cases, you will see a determinant is not equal to 0. In fact, this is my standing challenge in my classroom. Class consisting of 70, 80, even 120, I checked. Okay, you write down any 2 by 2 matrix or 3 by 3 matrix with random. Okay, almost always you will get the determinant non-zero. It is a non-singular matrix. What is the advantage? We are going to see that. So if I think of V1 to be, let us look at the first row AB, V2 to be the second row CD. Okay, then this V1, V2 is a basis. And similarly, look at U1 equal to the first column AC and U2 equal to the second column BD, then U1, U2 is a basis. Or if you want, you can also write it like this, AC and BD. Okay, if you want a row vectors, okay. If you think of R2 as row vectors, then you can think of write this column as a row, AC and BD, then this will also be a basis. Okay, let us verify it in a minute, but try to understand what I have said. Take any 2 by 2 matrix, write it randomly. It's okay. Most of the cases determinant is non-zero. If that be the case, take the row vectors, then the row vectors will form a basis. Or take the column vectors. If you want them, write it as a row vectors again, then that will also be a basis. So given any non-singular matrix, 2 by 2 matrix, you seem to have produced two bases. You understand? Now, next thing, I have to say why they are linearly. So I have to show why it is independent. Okay. So I have to show, let us look at only V1, V2. So V1 consists of AC and AB, right? AB and CD. Okay. Why this is a basis? Notice that these two vectors, I want to claim these are linearly independent and spanning. Okay. If you know the dimension, that's already good enough. If you assume that you know the dimension concept, then dimension R2 is 2. And if I show this linearly independent, then it has to be a basis. Right? You understand that? Okay. Okay. Right. So why it's linearly independent? Suppose I give two vectors. When are they linearly dependent? Do you remember that in linear dependence independence video we had already seen? Given V and W, they are linearly dependent if and only if one is a scalar multiple of the other. Okay, T times V, or V is S times W, some such thing. Yeah, they are linearly dependent implies one is a scalar multiple of the other, right? So that means, let us assume with our laws of generality, my CD is T times AB. Then what is the matrix? The matrix is going to be AB, T times A, T times B. And what is the determinant? Determinant is 0. That's a contradiction. You show that? Therefore, this is linearly dependent. In a similar way, you can also show these two vectors AC and BD are linearly independent. Okay. Therefore, we have shown that V and W are linearly dependent. Linearly independent. Sorry, I keep saying linearly independent. Linearly independent vectors in R2. Okay. As I said, if I know the dimension concept, the dimension of R2 is 2, and I had already produced a two element set which is linearly independent. Therefore, this must be basis. Suppose I did not know the dimension concept, then I can ask, can I show it's a spanning set? That's also clear, because what do I want? Give me any two a vector xy in R2, then I have to write it as a linear combination xy equal to C1 times AB plus C2 times CD. What I have to check? C1, C2 or NR. So I have to find whether there exists C1, C2. That means you can write it as C1, okay, AC1 plus CC2, right, into BC1 plus DC2. This must be my xy. Notice that xy is not variable now, it's a fixed vector, and C1 and C2 are unknowns. So I have to solve for the equation x equal to AC1 plus CC2 and y equal to BC1 plus DC2. Right? Unknowns are C1 and C2 are unknowns. Can I solve for that? I'm sure from your high school, you know you can solve for this if you know AD minus BC is non-zero. Right? In your high school and again in your BSc first year, you might have seen such a thing. So you can solve for it. since the determinant AD minus BC is not 0. Okay, so what I have shown now, I have shown that this vector v1 v2 is linearly independent as well as a spanning set. Therefore, it's a basis according to one of the criteria for the basis. Okay, in the last thing on equivalent definitions of basis, we have seen one of the criteria for a basis is linearly independent and spanning. Are you happy with that? Okay, so what I have shown now? Now, how many bases I have given you? I have given you as many bases as you can write 2 by 2 matrices with the determinant non-zero. That's it. And each of the matrix very likely to produce two distinct bases. It may happen that they below give the same thing. Okay, but let's not worry about it. Okay, so now can I generalize this? More general thing? Yes, I can do that. So I will quickly say that. So suppose I have an Rn. Okay, how do I generate a lot of bases? Again, the same thing. Take any matrix A, right? Write it as column rows R1, R2, Rn, or as columns C1, C2, Cn. Okay, these are the column or the row. And assume determinant of A is non-zero, right? Then this R1 to Rn, or if you think of Rn as row vectors, okay, then C1 transpose, Cn transpose, because these are all column vectors. When I take transpose, it becomes row. Okay, this collection, these are bases of Rn. So again, even in, for example, n equal to 3, what all you have to do is you write down a 3 by 3 matrix. Make sure you choose it in such a way that determinant non-zero. Then the rows are going to be a basis, or take the columns. If you want to take the transpose so that they become rows, they will also be a basis. That's it. Proof is exactly similar to what we did earlier. I'll quickly say that. I'll not pass too much time on that. So why this set, let us say R1 to Rn, okay, this is linearly independent. Okay, I want to check why it is linearly independent. I'm sorry, I should have given this as a pause review. Proceed. Okay, if you are not done, please go back and understand the 2 by 2 case first, then come to this R2 case first, and then come to this. Okay, suppose if they're linearly dependent, so okay, assume false, then this is linearly dependent. Okay, now again, in my video on linear dependence independence, I have shown that a finite set is linearly dependent if and only one of the vectors in that set is a linear combination of other vectors. Okay, please recall that means there exists a J without loss of generality. Let me say J equal to N, so that Rn is a linear combination of, let us say, C1 R1 plus Cn minus 1 Rn minus 1, right? But then look at determinant of A. Determinant of A will be determinant of R1, R2 and Rn, but that's equal to determinant of R1, Rn minus 1 and then C1 R1 plus Cn minus 1 Rn minus 1, right? The last row is linear combination of the earlier rows, therefore you know the determinant is 0. In case you are not sure, this is same as determinant of R1 C1 R1 plus determinant of R1 R2 C2 R2 plus determinant of R1 Rn minus 1 Cn minus 1 Rn minus 1. Okay, therefore this is C1 times R1 to R1, this is 0. This is C2 times R1 R2 to R2, and this determinant of, say, this determinant will be Cn minus 1 times determinant of R1 R2 Rn minus 1 Rn minus 1. Therefore this is 0 plus 0 plus 0 equal to 0. You understand? That's a contradiction. Okay, therefore we conclude that this is linearly independent. So this is done now. Now you can again using Cramer's rule. If you have done linear equations, you know Cramer's rule implies this R1 to Rn is a spanning set. Okay. If you already know the dimension concept, dimension of Rn is n, and this set number of elements in R1 to Rn is n. Okay. Therefore, and this is linearly independent. Therefore, any n vectors which are linearly independent in an n-dimensional vector space is a basis. Therefore, this is a basis. Okay. Whichever way you like, you take that. So, have you understood this? So, pause, review, and proceed. So, in each of the cases, it's easy for you to produce as many bases as you want. That's the advantage. It's unfortunate. Many teachers and textbooks do not explain how to generate more. Whenever you think of a basis, students always think of U1, U2, Un and nothing more. I hope this helps you to do that. Next. Okay. Now, next, more generally, suppose I start with the finite dimensional space VD, and suppose, okay, I will call it E1 to En, but this need not be Rn. You understand that? Some base is E1 to En. Don't think of the standard basis because you don't know what is V. Okay. If you want, let me fix. Okay. Students always have a problem. Let me call it U1 to Un is a basis. Basis of V. Okay. Right. The moment you introduce a basis, then there is a system of coordinates introduced on V is introduced. How is it done? Again, let me just look at geometrically. Suppose this is my U1 and this is my U2. Okay. They look like orthogonal, but that's not necessary because there is no at present this is U2. Okay. All right. So the idea is to start with any vector now x. Okay, it's going to be a linear combination of two vectors. Okay, by a law of parallelogram. So this will be this vector. Any vector V will be linear combination. If you don't understand such things, ignore. Okay, I'm going to explain that in a minute. So, given a vector V, we know that I can write as a linear combination of these basic vectors C1, Ci, Ui, I equal to 1 to n. So, since I want to say it's a system of coordinates, what I want to say is I can write it as x1 u1 plus x2 u2 plus xn un. Notice that V is some space you don't know, need not be Rn, and u1 u2 n is any basis. Then I can always write it. Then this V, I write the system of coordinates. I call this x1, x2, xn as a system of coordinates. That is coordinates of V with respect to the ordered basis. Because there is an order in the basis. This is the first element, this is the second element, this is the nth element. Therefore, this is the first coordinate, this is the second coordinate, this is the nth coordinate. How did I get the nth coordinate, ith coordinate of V? That is, you write V as a linear combination of u1, u2, un, x1, u1 plus x2, u2 plus xi, ui plus xn, un. Then the coefficient of ui is called the nth coordinate. Is that clear? Yes? Okay. For example, just as example, let us look quickly. Okay. Suppose I start with x r2 and my u1 is now 1, 1 and my u2 is 1 and minus 1. Right. Now you give me a vector x, y in R2. Remember when I write xy in R2, with respect to the standard basis x e1 plus y e2. Anyway, so what do I want now, right? Xy equal to, okay, some x1 u1 plus x2 u2. But what is x1 u1? It is x11 x1 x1 plus this is x2 minus x2, and this is x1 plus x2 and x1 minus x2. You understand? These are all vectors. How do I add two vectors in R2? By coordinate wise. You follow that? Therefore, what do I want? I want xy, the ordered pair xy must be equal to the ordered pair this. That means x1 plus x2 must be equal to x, and x1 minus x2 equal to y. Therefore, this implies adding these two, I get 2x1 must be x plus y. That is x1 must be equal to x plus y by 2. And subtracting one from the other, I get to 2x2 equal to x minus y. Therefore, x2 equal to x minus y by 2. You understand that? Therefore, the vector xy is plus x minus y by 2 into u2. Then with respect to u1, u2 basis, the coordinates of the original vector xy are not x comma y. The coordinates are x plus y by 2 and x minus y by 2. You understood this? Okay, PRP. So this way of thinking a basis, given a basis, it gives rise to a system of coordinates. Okay, on V. Okay, this is the geometric thing. Okay, that is going to help us to find bases in some spaces, vector spaces. And also it allows us to guess, okay, what is the dimension. You see that in general in linear algebra, to find the dimension of vector space, you have to exhibit a basis and count the number of elements. Right? Now we are essentially reversing. Okay, any basis gives rise to coordinates, right? Therefore, so if you give me a vector space, I will see how many coordinates I need to locate a vector. Okay, that tells me how much, what should be the dimension. Number of coordinates is what I think of the dimension. And using that fact, I will actually construct a basis. You see that? It's a completely reverse process. It's a kind of discovery. You are discovering a basis. Whereas in general, a basis given, you verify it's a basis. That's a verification. Okay, please understand. You will look at it in a very simple way. Okay, let us look at this. Suppose, let us look at W to be the set of vectors of the form xy in R2 so that x equal to y. So you know this is a vector subspace of R2. Okay, this is very easy to check. It's a vector subspace, right? This is exactly the picture will be something like this. Okay, this is your W. Right. Now this is a vector space in its own right. Now to find a vector here, how many coordinates I need? As a vector in R2, I need two coordinates x and y, but I know this vector lies on this W. There, if I know the x coordinate, I also know the y coordinate, or other way around. If I know the y coordinate, I also know the x coordinate. Therefore, how many coordinates I need to locate a point in W? I need only one coordinate. If you know one of the coordinates x or y, I know the other coordinate. Therefore, what should I expect? How many elements should be there in the basis? So I expect the basis of W, that is dimension of W, must be equal to 1, and hence basis should have only one element. Now how do I get a basis? That's very easy. Let us look at, therefore take a vector W in W, then it is of the form x comma x. But this I can write as x into 1 comma 1. You understand? Therefore any vector W can be written as some scalar multiple of 1 1. You understand that? Any vector W can be written as a scalar multiple of this fixed vector 1, 1. Therefore, what does it suggest? It suggests take U equal to 1, 1 and the singleton U is a basis of W. Okay. Okay. Now to check it's a basis of W, what are the things I have to do? I have to say it's linearly independent. That's clear because the vector is non-zero. Any singleton vector, non-zero vector is linearly independent set, right? If you use a non-zero vector and the singleton U will be linearly independent set by very definition. Because if you say Cu equal to 0, since U is not equal to 0, this implies C equal to 0. This is one of the first corollaries after the definition of vector space. You must have seen this, right? Therefore, this is a linearly independent. Next, and we just now saw any vector is a linear combination of this particular vector, namely scalar multiple of that. Therefore, it's in particular linear combination, right? Therefore, it's a spanning set. So this singleton is also spanning set. Okay. Therefore, by one of the characterization of basis in my video on equivalent definitions of basis, linear independence plus spanning set is same as saying a basis. You see that in particular, since this is a basis, I know the dimension of W is 1. You follow that? Something very strange is happening, right? I look at geometrically how many coordinates I need. That tells me intuitively what should be the dimension. Then from that I get how to find a basis. Then I check it's a basis. Therefore, I know the dimension. Okay, just think about. Enjoy this. As a very easy thing, let us do something more. Let us look at the set of 2 by 2 symmetric matrices. Okay, in R. So that B equal to C. It says that is symmetric matrices, symmetric 2 by 2 matrices, right? If you give me an arbitrary matrix A, B, C, D in a 2 by 2 symmetric matrix, A could be anything, B could be any real number, C could be any real number, D could be any real number. So I need essentially 4 coordinates to describe any vector A in 2 by 2 real matrix. It needs 4 coordinates. You understand that? Therefore, the dimension of M2R, I should suspect, should be 4. That is very easy because I can write A, B, C, D as A times 1, 0, 0, 0 plus B times 0, 1, 0, 0, etc. plus D times 0, 0, 0, 1. Okay. So this is your basic vector, call it E1, this is your basic vector E2, this is your basic vector E3, this is your basic vector E4. You can check they are all linearly independent, they span. That's very easy. Spanning is what I have shown. They are linearly independent because this is equal to 0 implies it is 0, 0, 0, 0. That means A is 0, B is 0, C is 0, D is 0. You understand? Right. Therefore, I know the set of 2 by 2 matrices, real matrices, okay, has dimension 4. Notice that by means of coordinates, I already know the dimension must be 4. And using that, I found out a basis. Right. You understood? Okay. Now let's go back to the 2 by 2 symmetric matrices. Just pause, review, then come to this 2 by 2 symmetric matrix. So now my W is A, B, C, D. A, B, C, D are in R, but B equal to C. Now, therefore, how many coordinates I need? Is there any condition on A? No. Is there any condition on D? No. But the moment I know B, I know what is C. Therefore, I need to tell you what A, B, and D are. Once I tell you these three, then you can write down the matrix, right? You understand? A equal to, let us say, 1, B equal to -1, D equal to 4, then I know how to write the matrix. 1, -1, this must be -1 and 4. That's a symmetric matrix. You understand? Therefore, what do I guess? Dimension of W must be 3. You understand this? Yeah? Now, how do I find a basis of W? That's very easy. Take any arbitrary matrix. How does it look like? In W, it is of the form A, B, B, D. I can write as C, but it may confuse you, so I'm writing A, B, B, D. You understand? But how will I write it? This I can write it as I said, A, 1, 0, 0. But then when it comes to B, this is 0, 0, 1, 0. You understand this? And D, 0, 0, 0, 1. These are also. You understand that? Yeah. Now notice that, is this an element of W? Yes. Now you know this is very important. Is this an element of W? Yes, because it's symmetric. And is this an element of W? Yes, it's a symmetric. You understand? Therefore, call this as E1, call this as E2, call this as E3. What I have shown now, I have shown any matrix A, B, C, D which is symmetric is a linear combination of E1, E2, E3. That means, okay, E1, E2, E3, the span of that, okay, this spans. It's a spanning set for W. Okay, and you have to check whether they are linearly independent to show it's a basis. That's very clear, because let us say A times E1, B times E2 plus CD times E3 is 0. That means this is 0, 0, 0. That means, okay, you understand that? Right? A of E1 plus B of E2 plus D of E3. What is this? This is A, B, B, D. But you say this is 0. That means this is 0 matrix, 0, 0, 0. What does it say? Equality of matrices say A must be 0, B must be 0, D must be 0. That means it's linearly independent. Therefore, this is the basis. Now, how many elements are there in the basis? 3. Therefore, dimension W is 3. Do you understand this? Pause, review, proceed. Before we go further, now let's look at, okay, another vector subspace W1, which is all skew symmetric matrix A, B, C, D, right? What is the skew symmetric matrix? Remember, if I give a matrix A equal to Aij, it's a n cross n matrix. When you say, would you say it's a skew symmetric? If for all ij, Aij must be equal to minus of Aj. Okay, then in particular, what will be A11? A11 must be equal to minus of A11, and that means A11 must be 0. And similarly, Aii equal to minus Aii, that means Aii must be 0. Therefore, any skew symmetric matrix, okay, will have 0, 0 on the diagonal. And if I have A12 here, then what will be? Let me write it. This is A11, which is 0. And A12, let us say A13 and A1n. Okay. And here it will be minus A21, because this must be. And A22 is 0. And this will be A23 and so on. This will be A2n. Now come to A31. A31 must be negative of A13, therefore it's minus A13. And A23 will be, this is A32, but A3 should be negative of A23, therefore it's minus A23. Do you understand? And A33 will be 0. This will be A3n. Now come to the last one. This will be AN1, but AN1 must be negative of A1n, therefore it's minus A1n. And this will be minus of A, this must be AN2, but that should be minus of A2n. Are you following? and so on. The last one will be 0, right? So you can see the pattern. The pattern is diagonal is 0, and if I know something here, aij, then I know aji. Aji is going to be minus of aij. This is the jith place. You understand? Think carefully. Okay. For example, 2 by 2, what does it mean? I have 0, 0, 0. I have a12, a13. This will be minus a21, a22 is 0, a23. Now I want a31, which is minus a13. A32 is minus of a23, and this is 0. You understand? Now what does it mean? This diagonal is 0. So if I know something above diagonal, then I know all the elements which are below diagonal. You understand? Because a12, if it's aij is there, I have to put minus aji. Therefore, that's not a new coordinate because it's predetermined. It's a new coordinate must be, it should be independent of what happened at ijth place. The moment I know what happened in ijth place, I know what is going to happen in jth place. It is predetermined. So it's not independent event. You understand that? Therefore, I have to know only these 3 coordinates. Then I know all the thing. You understand? This is a 3 by 3 matrix. So how many coordinates I need? As a matrix in M3R, I need 9 coordinates. But the moment you tell me this is skew symmetric, then I am better off. I know all the diagonal elements from 0, and if I know whatever is above the diagonal, then I know what is going to be below the diagonal. Above the diagonal, how many elements are there? There are 3 things, and they are independent. I can take a1 to be any real number, a13 to be any real number, a23 to be any real number. Therefore, I need 3 coordinates. You understand? Therefore, what I think, dimension of W1 must be equal to 3. So more generally, for any n, okay, I am looking at W1 to be skew symmetric matrices, okay, of size n cross n. Then what do I know? All the diagonals are 0, and I have aij here. Then I know what is aji here. Okay, this is ijth place. This is the jith place. This is the jith entry rather. That's the way you say, right? Ijth entry, this is jith entry. Right? So how many are there? Notice that this is 0. This is the first one. This will be 2. This will be 3. This will be n. Therefore, the one before that will be n minus 1 elements. And this will be n minus 2 elements. This will be 2 elements. This will be 2 elements. 1 element. So how do I need? How many coordinates do I need to describe a skew symmetric matrix? I need here a11, and here I need 2, 2 up to n minus 1. Okay, these many coordinates are needed. This I know, n into n minus 1 by 2. So I need these many coordinates. Therefore, dimension of W1, I should suspect it should be n into n minus 1 by 2. Let us check it. When n equal to 3, does it tally with what we found out? When n equal to 3, it is 3 into 3 minus 1 by 2, that puts 3. That's correct. Yeah. So we know dimension. Even before we have found a basis. Now, how do I find a basis? Okay. To keep life simple, I'll do 3 by 3 case. The same thing can be done n by n. You should sit with your friend and check it. If you want, I can write it, but it's much easier. So what do I do now? You see that? Now notice that when I say above diagonal, if I say ijth entry, what is the relation between I and j? Relation between I and j. Let us look at that. This is a11, this is a12, and a1n. You see that I is less than j. Here a21, a22, above diagonal will be a23 and a2n. You understand? Therefore, I must be less than j. Do you understand? Yes or no? Therefore, in ith row, how many I will have? That's what you are asking. You understood this? So ith row, this is the first row, I'll have n minus 1 element. In the second row, I'll have n minus 2 element. In the nth row, I'll have nothing. Whereas n minus 1th row, I'll have 1 element. Are you following? This n minus 1th row. Are you following? Make sure, please do that. Okay, these are the things which are free for me. They are independent. So in the first row, I can fill any one of the n minus coordinates with any real number. Therefore, n minus 1. And here I can choose any one of the thing. Okay. So in here, so how many elements I can choose? N minus 1. Notice that there is no product. You are just simply summing n minus 1 plus n minus 2 and n minus 3. Okay. Right. Therefore, I can write it for I less than j and 1 less than I equal to I and less than. This is j, therefore I must be at most n minus 1. You understand that? I can be at most n minus 1. I could be 1, as we saw there. Okay. So you denote Eij to be the one with ijth entry is 1 and jith entry is minus 1. This is jith entry. This is ijth entry. You understood that? Yeah. For example, in n equal to 3, what do you have? I have 0, 1, 0, and this is 1, 2. Therefore, this will be 2, 1 will be minus 1, 0, 0, 0, 0, 0. The rest are all 0. And the second one will be 0, 0, 1. And this is 0, 0, 1. And this will be 3, 1, therefore minus. And the third one, what will I have? Okay, this is 0, 0, 0. Now I have this. Okay, this I already know. This is 0, 0. I have 1. Then this must be 2, 3. Therefore, 3, 2 will be minus 1. So this is my E12. This is my E13. This is my E23. These are the 3 basic vectors. Okay. Now it's very easy for you to check this Eij 1 less than or equal to I, strictly less than j, less than or equal to n. This forms a basis. It's a linearly, it spans by very constructions, and they are linearly independent in W1. Okay, therefore dimension of W1 is the number of elements. What is the number of elements? Once I choose I equal to 1, there are n minus j which are greater than, so on and so forth. Therefore, it's n into n minus 1 by 2 as I already done. So you see that. So we have found a basis. Basis comes later, but dimension we found out earlier. And finding that helped us to write down a basis. This is the beauty of this way of thinking geometrically. So pause, review, proceed. Okay. As a very quick example, let us look at symmetric matrices of n cross n. What does that mean? This means Aij equal to Aji for every ing. That means I have no idea about this. There can be anything. But the moment I know what is A12, I know what is A21. If I know, the moment I know what is A1n, I know what is the AN1. A21 is same as A12. AN1 is same as AN1 is same as A1n. You understand that? Yes? Right. Therefore, what does it say? Now the diagonal elements can be anything. They are not 0 as earlier case. They can be anything. And this is A12, A1n. So in the first row, I could choose any real number for A11, choose any real number for A12, and choose any real number for A1n. Therefore, there are n elements. Now let's come to A21. Here it is already determined. Therefore, I can only choose A22, A23, A2n. Therefore, these n minus 1 elements, I can choose any real number. Therefore, the first row, there are n coordinates. For the second row, I have n minus 1 coordinates. Last row, I have 1 coordinate. Okay. Therefore, how many coordinates I need? to determine an n cross n symmetric matrix. N plus n minus 1 plus n minus 2, etc. plus 1. That is n into n plus 1 by 2. Okay, this therefore dimension of symmetric matrices, call it Sn, is n into n plus 1 by 2. Now can I write down the basis? Yes. Again you look at Eij, but then what is Eij now? When I equal to j, this is again 1 1. You see, when Ei, so let's say Ei equal to 1 at ith 1, sorry, Ei equal to 1 at the diagonal element ith element entry. The rest are all 0. And Eij for I not equal to j and assume as 1 I less than j less than or equal to n, that is going to be, okay, 1 at ijth entry, 1 at ijth entry, and 1 at jith entry. You understand? Okay. Then how many are there? This is, as we saw, n into n minus 1 by 2 plus this n. We had already counted, but I'm just doing it again another way. This is n into n minus 1 by 2 plus 2n. That is n squared minus n plus 2n. That is n into n plus 1 by 2. Yeah. So we have found it. Please check this is spanning, which is easy, and plus linear independence. So this forms a basis. Okay. So I have another 10-12 minutes. So let me look at another example. Okay. For more examples, you should look at my book, but I think I will stop with this example. Okay. This should give you enough idea. Okay. Once with this idea, you should try on your own and look at my book and learn something more. Let us look at R8 now. Okay. In this, I look at the vector subspace x1, x2. So W equal to x1, x2, x8. But what do I want is I want all odd coordinates should be equal. You understand? And among even coordinates, I want x2 must be equal to x4 and I want x equal to x8. You understand this? This is my W. You can check this is a vector subspace. Subspace of R8. Right? x1, x2, x3, x4, x5, x6, x7, x8. All coordinates are accounted for. Now just to have a look at how many coordinates do I need to express. If you give me a vector W in W, how many coordinates I need? To locate a vector W in W. Yes, I'm sure all of you will know the answer. Yes, because if I know x1, I know x3, x5, x1. Therefore, I need one coordinate to find all odd coordinates. When it comes to this, if I know x2, then I know what is x4. If I know x6, I know what is x8. Therefore, how many coordinates I need? I need to know only 3 coordinates. I have to know what is x1, what is x2, and what is x6. That's it. Therefore, I expect the dimension of W to be equal to 3. Do you understand this? Yes. Right? Now, how will I do that? Okay. See, we got the dimension beforehand. No basis, nothing. Now, how will I do that? That's very easy because let me write, take any vector W in W. How does it look like? It looks like x1, x2, x3 is x1, x1, x4 is x2, x2, x5 is x1, x1, x6 is independent, and x7 is x1, and x8 is x6. This is an element of W. You understand? Now it's very easy for me. Therefore, if I take x1 out, what happens? 1, 0, 0, or x1, sorry, x1, 1 and 0. This is x 5, right? Yeah, 1, third, 4, fifth, yeah, 0 and 0, x7, 1 and 0. Plus, take x2, then I'll have 0, 1, 0, 1 here because x2 and 0, 0, 0, 0. And next will be x2 times x6 into 0, 0, 1, 0 and 1. You understand this? This will give me x1 in the odd places. This will give me x2 in the second and fourth coordinate, and this will give me x6 in the sixth and the eighth coordinate. So I got everything. Therefore, what do I have? Call this as u1, call this vector as u2, call this vector as u3. Then u1, u2, u3 is a spanning set for W, right? Okay. And here, is it linearly independent? Yes, because if x1 times u1 plus x2 times u2 plus x6 times u3 equal to 0, that is x, you want to call it a times u1 plus a1 times u1 plus a2 times u2 plus a3 times u3 if you want. Okay, that is going to give me a1. You understand that? And a2, this will be a1, this will be a2, this will be a1, this will be a3, this will be a1, this will be a3. But that is equal to 0. Let us say it's equal to 0 vector. That means equating coordinate wise, component wise, what you find is a1 is 0, a2 is 0, a3 is 0. I simply did with respect to x1, x2, x6. This equal to 0 will imply this is 0. That means x1 is 0, x2 is 0, x6 is 0, right? Therefore, it's linearly independent. You understand that? Therefore, this is the basis. And how many elements are there in the basis? 3 elements. Therefore, what is the dimension? 3. Isn't it funny? Good. I hope you liked it. There are a lot more simple-minded examples in my book. Please do that, because as I said, this is an introduction for you to think the correct way, okay, the easy way, but you should follow it up, okay? So you please go back to my book and look at a few more examples and exercises and work them out. And please do discuss with your friends, okay? In case you get confused, each can help the other, or both of you can get confused, but then there will be revelation, okay? There will be all of a sudden a flash. You will enjoy. Okay. Have a good day.